Again, we're in our unit called quantum physics. We're not going to hit quantum yet. We need to learn all the preliminaries. Last time we were talking about waves, and the important property we're going to focus on today is the fact that two waves can occupy the same place at the same time. So we saw the waves coming in, bouncing off the barrier and passing through the incoming waves and going right through them. And there's going to be a moment where these two waves will be overlapping with each other. That's where our focus is today. We're going to call this combining waves. The idea is known as superposition. It's when you have more than one wave at the same place at the same time, like you see in this pond with lots of ripples caused by raindrops. The waves from one raindrop are superimposing on the waves from another. Superposition, superimposing. Two waves, same place, same time. And you can see how the waves go right through each other, but when they're overlapping, that's called superposition. There's two main things I want you to remember about ways they can superimpose. In this case, we have a red wave and a blue wave. Again, we're not talking about the actual colors, but a wave represented in red and a wave represented in blue. They are exactly 180 degrees out of phase, so that as the red wave is going positive, the blue wave is going negative. The combined wave is going to be no wave at all, because these two waves cancel out. This is known as destructive interference. With sound waves, this means we have two sound waves producing silence. With light, these would be two light waves producing darkness. Notice, in order for this to work, the two waves have to have the same amplitude, they have to have the same frequency, and they have to be 180 degrees out of phase with each other. We can produce this electronically in our noise-canceling headphones. We talked about this a little bit last year. You have a noise created by an external source. It's picked up by the microphone inside the headphones. The computer then creates another wave that is 180 degrees out of phase with the original. These two waves will superimpose and produce silence. Noise-canceling headphones. They don't muffle the noise, they cancel the noise using destructive interference. Okay, the next type of overlapping is when they overlap in phase, and this is called constructive interference. You have a red wave and a blue wave, and it's hard to see them both because they're right on top of each other. They have the same frequency, the same amplitude, and they are in phase. The combined wave, as you can see, has twice the amplitude of the original wave. It's constructive. With sound, this would produce a louder sound, and with light, it would produce a brighter light. Constructive interference, same amplitude, same frequency, in phase. Okay, so this phenomenon of these overlapping waves is known as interference. If it's perfect overlapping in terms of the way they're lining up, it's constructive. And if they're 180 degrees out of phase, it's called destructive interference. I'd like you to now see how we can produce this using speakers. We can do the same thing with light. Okay, so we're going to have two speakers producing an identical wave, one frequency. We're not talking about a sound that has lots of frequencies in it, but a single frequency sound, and we're going to put the speakers different distances away from the person. And this is called delta X, is the difference between the two speakers. So the blue wave will have traveled a delta X farther than the red wave. Keep this in mind, it's very important. All right, so let's take a look. So let's start our speakers making sound. One frequency, both the same frequency, both the same amplitude. You can see they are arriving at the person out of phase. Not perfectly out of phase, but not perfectly in phase. So we have interference, it's just not constructive or destructive in terms of total. It's not totally constructive, it's not totally destructive. Okay, but if we position our speakers just right, we can reach a scenario where the two waves are destructive. And you'll notice it's not just random, but we move these speakers so that the difference between their distance is equal to 1/2 of a wavelength. Speaker 2 is half a wavelength farther back than speaker 1. That will always produce destructive interference if the waves are produced synchronously. That is, they are produced at the same time with the same frequency and the same amplitude. Okay, what we're going to do now is we're going to move one of these speakers backwards. And as we move it backwards, we can see that we switch from destructive interference to constructive interference. It's because we moved the speaker back another half wavelength. So now the difference between the two speakers is 1 full wavelength. So half a wavelength made destructive, a full wavelength made constructive. So again, constructive interference. And then if we continue to move it back, it will turn destructive again. We are now 1.5 wavelengths. 1.5 wavelengths apart in terms of our delta X. So destructive happens at half a wavelength, 1.5 wavelengths, 2.5 wavelengths. Anytime we have an integer plus an extra half wavelength, we get destructive interference. We get constructive interference if our delta X is 0. Now the two waves are produced at the same time in the same place. They're guaranteed to be in phase, regardless of what the wavelength is. So delta X equaling 0, that's always constructive. So as a summary, constructive happens at 0, it happens at 1 wavelength, it happens at 2 wavelengths, and it happens at all integer number of wavelengths. Okay, destructive happens at half a wavelength, 1.5 wavelengths, 2.5 wavelengths, and so on. Okay? Constructive, destructive, back to constructive. Okay? So this pattern will repeat itself almost indefinitely. If you'd like a little summary, when the two waves travel the exact same distance, so the difference in distance is 0, it's constructive. If it traveled an extra half wavelength, as you can see right here, half a wavelength back, that's destructive. And then another half wavelength to give us a full wavelength. You can see speaker 2, extra wavelength. This produces constructive again. Okay, so how do we do this in real life with light? We use a device like this one you see here. It's called an interferometer. And the pieces to the interferometer you can see are a half silvered mirror. What that means, half silvered, is that half the light will hit it and go through, half the light will hit it and bounce off. 50% goes through, 50% bounces off. It's like the mirror they might have in a store where the manager will be able to see out of the mirror, but people in the store might think that it's actually just a regular mirror. All right? Then you have 2 regular mirrors that reflect all the light. One of these 2 mirrors is usually on a movable platform. And then you have some sort of device like a screen or a sensor that can pick up the light. So draw this out. We've got our light beam come in, hit the mirror. Half of it will follow path 1. Half of it will follow path 2. Half of it hits the top mirror, half of it hits the side mirror. That light that hits this mirror will then go through, and half of that light will come through to hit our sensor. The other half bounces back the direction it came from. We don't care about that light. Same thing here. All the light bounces off, half of it hits the mirror and bounces down to the sensor. We don't care about the part that went through the half mirror again. So we have beam 1 and beam 2. What we've effectively done is we turned one beam of light into 2 beams of light. And since they had the same source, they're going to have the same frequency, and they're going to be in sync with each other when they started out. The thing is, they may not have traveled the same distance. Especially if I could have one of these mirrors on a movable platform, I could move it backwards so that beam 2 will have traveled farther than beam 1. And by doing that, I could start with a delta x of 0, meaning both beams traveled the same amount, and have a bright constructive light. And by backing it up just a tiny little bit, I can get it to turn dark. And I back it up a little more, it becomes bright. And by measuring how far I move the mirror, I can figure out the wavelength of the light, a very efficient tool for figuring out the wavelength of light. So again, it looks something like this: half silvered mirror, fixed mirror, detector. Here's what it might look like in real life. You can see the mirror on the angle. Okay, and we can see a beam over there on the wall, so we can see what it looks like. You can see a split screen here. As we turn the micrometer to back the mirror up ever so much, we can see the pattern that we're seeing go from dark to bright to dark to bright. Okay, so when you see the dark circle in the center, that's telling you that you're getting destructive interference occurring. When you're, like it is right now. When you move it so the inner circle is red, that's telling us that constructive interference is occurring. Okay? And we can figure out the wavelength of the light by moving that mirror ever so slightly. It's called an interferometer. Tomorrow we're going to examine another thing that can do the same idea of taking one beam of light and splitting it into multiple beams that we could then recombine to produce this interference. It's a phenomenon known as diffraction, and we will be talking about that tomorrow.